This is a presentation that will be not looking sort of backwards to necessarily how to implement current code standards, but really quite a ways looking forward of what is coming on this type of building. And so it's a unique opportunity to see how the code is being developed and what you might see in the next 1 or 2 code cycles. And so the idea of new provisions for one-story buildings that have these flexible diaphragms with rigid walls or rigid vertical elements is nothing new, but it just hasn't really found its way into the code until some research was finally done, and we've learned a lot from it. So I'm going to be providing some of the research and how it was laid out, and then Kelly's going to take the last half and then show in her Part 2 series a design example on how to implement what we've learned. So when it comes to these types of buildings, they're quite ubiquitous as far as warehouses, logistics, and especially with e-commerce that we have happening, and Amazon and Walmart and all the big box stores that are also using large logistical operation centers. These buildings are getting more and more common and larger, and it's important that we look at its seismic performance. The development of this methodology is going to be my part of the beginning of this presentation, and it's really, when you look at this picture here, you see a lot of the same type of building types, and a lot of these will behave quite differently than what the building code currently envisions. So Part 1, I'm going to be giving you an introduction to this building type and the behavior and issues associated with it, then followed by the numerical modeling research that has gone under for coming up with an improved performance. And it's going to be looking at primarily, in my presentation, the wood structural panel diaphragms that are so common on the seismically active West Coast. But then I'm also going to talk a little bit about the bare steel deck diaphragms and what they've been doing in regards to this exact same issue. And there's some additional side studies that were looked at. Since we had a nice, robust computer model, we decided to look at some of the wall anchorage issues that have prone this type of building type in past earthquakes, as additional to the building heights, how different height buildings might be affected in the performance, and also a separate P-delta study that was done to see the second order effects that might occur in these types of buildings. So there's our outline for the first hour. So let's talk a little bit about the numerical modeling that was done on this type of building. So the rigid wall flexible diaphragm, I'm going to use that abbreviation RWFD, or you're going to see it, but it can really go for brace frames as well as rigid walls. They're going to behave very similarly, and these are typically buildings of concrete and masonry walls that are relatively rigid in plane, and then they have large diaphragms that are very flexible. Classic diaphragms on the West Coast, about 80% of these building types are wood structural panels. So that's going to be your plywood, your OSB, typically nailed in a blocked wood diaphragm fashion, and they're typically constructed with a panelized wood roof system. And these are very flexible in plane, and this is what your big box retailers such as Costco, Target, Home Depot will typically have buildings of this type. In addition, we have distribution centers that serve these big box retailers as well as other retailers throughout the United States in warehousing, logistics, that are getting larger and larger as they consolidate their operations. Here's an example of a building that is 1.2 million square feet. It's located in Phoenix, Arizona. It has the wood deck diaphragm. The building is so large that the curvature of the earth causes one side of the building to be about an inch lower than the other, and it has one of these interior concrete walls for the shear element. And actually, it's not just a shear element, but it's also a firewall for a maximum foreseeable loss from one side to the other. These buildings are massive. But the question gets to be is, how do these buildings behave? Well, luckily, since they're flexible diaphragms and they're typically deforming from a shear standpoint instead of a flexural standpoint, they're going to behave as compartmentalized little rectangles between the interior brace frame or the interior shear walls. Those interior shear elements compartmentalize the behavior to a large extent. So we're going to be looking at the behavior of these different rectangular segments. And this behavior is dominated by the diaphragm, where the deflection of the diaphragm is significantly more than the deflection of the wall. And these large deformations in the diaphragm are associated with a long period. And so you can think about that this element in the building at the roof actually has its own frequency of vibration that is completely separate than the vertical shear walls, which are going to have a much smaller or shorter period. Now, this behavior causes the seismic response to be quite different, and the seismic response of the diaphragm, and really a lot of the building, is going to be dominated by that flexible diaphragm where a lot of the load resides. And so if its frequency is quite low or its period is quite long, it's going to be behaving differently than the short walls in a seismic event. Just like the period of a tall building is going to behave quite differently than the period of a short building.